All right, so continue with what we have here. Okay, so it's gonna be 3 times 2 square root of x plus 1 over 2 times negative cosine of 2x plus a constant c. Okay, so that's about those 5 examples. Again, guys, if you take the derivative of this, guarantee you're gonna get the original p of x. Okay, I'll maybe just do this part. Capital P. Okay, capital P x. Here. Okay, so those are the examples, and the process of finding the collections of the antiderivative, we actually have a name. It's called the integral. Okay, an integral, and more accurately, we call this process is called an indefinite integral. And let me show you some examples. I can just leave 1 or 2 here. So let me erase this. Okay. Okay, so how do we describe those in terms of the new definition, the integral notation here? Fairly straightforward, guys. Okay, so given fx, trying to find its general antiderivative, which is capital Fx, can be denoted into this way. The big integral sign, 1 over square root of x dx. Okay, so this integral means find the antiderivative of 1 over x with respect to x. Okay, and we know that the solution is already here, which is 2 times x to the power of 1 over 2 plus a constant c. Okay, so this is what we call the indefinite integral. Okay, of course you can do this one right into integral x to the power of -7 dx. Gonna be x to the power of -6 over -6 plus a constant c. Okay, so this is the integral notation here. Okay, so really it's an easy way to write the antiderivative form. Okay, calculus really is about the derivative and the integration. Okay, and also guys, to solve this integral here, we can also have a process which is do the integration. Okay, what's the integration of 1 over x square root of x with respect to x? Well, 2 times x to the power half plus a constant. Okay, so this is notation here. So let's move on to here to introduce another topic that's related with the antiderivative and the integration. Okay, so to find the antiderivative or to solve for an integral problem, it is equivalent to see, okay, think about this. If we have an equation, left side is dy dx, okay, which is the derivative of y with respect to x, equals f of x. And do you agree that to find y, right, which is to solve for this equation, is exactly the same to find its antiderivative for this function, right? So, but we have a name. This type of equations is called the differential equations. Okay, differential equations. Well, I think for here, this part the name is constant. Differential equations. Okay. And also, guys, if you embedded a condition, in other words, when x equals x0, the corresponding y equals y0, we have also have a name. This is called the initial value condition here. Okay. So combined with the differential equation and this initial value condition, we have name. This is called an initial value problem, also called so the also short for, if we have dy dx, let's see, equal fx, and then we have y of x is 0 equals y of 0. This whole set we always call IVP. That means initial value problem. Okay, IVP. And there is a homework here, guys. Please read section 4.8, example 5. Okay, in the textbook. It could be one of the problems in our final. Okay, so maybe let's look at one of the examples here, guys. And later on, I'll also introduce what is called the general solution, what is the particular solution. Okay, so let's still in this board. Look at this problem. So if we have dy dx equals x squared, okay, equals x squared. And if we want to look at this, guys, do you see that this is what we call a differential equation? Okay, first order differential equation. And you see, you are looking for how do we solve this? Do you agree that to solve this differential equation is equivalent to trying to figure out, so y actually equals trying to find an antiderivative, right, of this function, which gonna give you its x cubed over 3 plus c, okay? And you can evaluate this, guys, right? So if you take the derivative with respect to x, do you see dy dx is x squared? So right? This, we have a name. It's called the general solution, okay, for this differential equation here, okay, for this differential. However, if I embed one initial value condition, for example, like this, I want to have, I don't know, y of 0, let's say equals 1, okay, y0 equals 1. So you see, guys, this is the general solution, y equals x cubed over 3 plus an arbitrary constant. However, when I put this initial value condition on, this c, it will not be arbitrary. In other words, we are actually looking for a particular value that satisfies this condition. But how do we figure out that particular value? Well, let's see. Since yx equals x cubed over 3 plus c, meanwhile, it also satisfies this. So y of 0 equals 0 cubed over 3 plus a constant c must be 1. Do you see that we can easily figure out our arbitrary constant is not arbitrary anymore. It must be equals 1 to satisfy this condition. Then we can get that, okay, the y of x is going to be x cubed over 3 plus 1, which this one not only satisfies this differential equation, but also satisfy my initial value conditions. And we have a name for this solution, which is, this is called a particular solution. Okay, particular solution. So, this is one of the examples. In fact, guys, think about it this. All the examples we just discussed can convert it into a differential equation, right? Because to find the solution of a differential equation is exactly same to find the antiderivatives. Okay, and the differential equation has tons of applications. Right now, the COVID-19, a lot of experts use differential equation to do the modeling and prediction, and um, and also part of my research work is to to use the differential equation to do the modeling about the smoking population groups. Some people smoke, some people don't. Some people may be temper smoke. Some people may be um, temper quitter. Some people may be power quitter. So those different groups, they interact with each other. So we use differential equation to build this. But anyway, just to let you know that it has tons of applications in real life about differential equation. Okay, so I'll stop here.